want to make sure we're all doing okay. It's good to see you guys here. Thanks for coming. Looks like we're missing a good number of people. I made enough copies for everyone, but I have this many left over, so it's too bad for them. And then we have that many quizzes not picked up either. So.
Can I have an extra one for someone that's not here?
Okay. Tell her, shame on you.
Thank you.
Okay. I hope she's all right. Okay. So anyway, you need one. You are here. That's great. Okay. All right. So this week is chapter 9. It's a heavy week. Okay. Last week was chapter 8. That was a heavy week. This week is also a heavy week. Okay. Next week is chapter 12. That week is lightweight. Okay. It's a little bit lighter, and we'll start to go over, start to do our review. And then the week after will just be all spent on review here. Okay. I'm very pleased with what's happening on the Facebook group. All right. So some of my answers may not be thorough enough for some of you, and so different students have been posting things. Good stuff there. So if you're not part of the Facebook group, or if you don't check it very often, I highly recommend looking at that and seeing some of the solutions posted there. So that's good. And so you guys got your third quiz back. Some of you, this marked an improvement among earlier scores, and others of you did not do as great. We got one more quiz and a final exam. Okay, so next week we have a quiz that's going to cover stuff in chapters 8 and chapters 9. Okay, next week's quiz is almost, you can think of it as like a mini final, okay? Because our final exam is very heavily focused on chapters 8 and 9, okay? It's like 70% chapters 8 and 9, maybe 10% chapter 12, and 20% stuff from before the midterm. But a good chunk of it is going to be in chapters 8 and 9. So next week quiz, which comes from chapters 8 and 9, is kind of like a light version of the final exam. All right. And so you'll get, after you take that quiz, you'll get a sense of how much you know or how much you don't know. Okay. I encourage you to practice and just make sure you can identify problems and know the steps and know how to work through everything. All right. Okay. Any questions or issues before we go on? Good. Okay. Great. All right. So I passed this table out. This is the T table. Okay. So next week for the quiz, you are going to need your T table, this table that I just passed out, and your normal table, which you should have already. Okay, so don't forget to bring those to class next week for the quiz, because you'll need them.
You mean the monomial?
Binomial? No, you don't need the binomial. You just need this table, the T table, and your normal table. Okay, so you know your normal table very well by now, and this is the T table. So the T table, maybe we will talk about using the T table first. Just learn how to use this table, and then we'll get into the meat of the chapter. All right. But I guess let me just start off with this. So this is chapter 9, and we are going to do hypothesis tests in confidence intervals. numeric variables. Chapter 8 and Chapter 7 actually was all about hypothesis tests and confidence intervals for categorical variables. You're dealing with proportions, because proportions only exist for categorical variables. Chapter 9, we're going to deal with numeric variables, and so we are dealing with means, standard deviations, things like that. Okay, so we're going to learn hypothesis tests and confidence intervals for numeric variables. All right, and so this is an always rule. Okay, always. All right, if you are dealing with categorical variables, you will use P, and if you are using P, you use the normal table. All right. This week, numeric variables, we are going to use mu for mean and standard deviation. So mu and sigma, and we use the T table. So categorical variables, normal table, you use the normal table. Numeric variables, the T table. If you're dealing with P, normal table. Mu, T table. Got that? All right, so the T table is very different from the normal table, okay? Alright, so when we dealt with the normal table, or we had proportions, if we had to do confidence intervals, what did I say? What were the numbers you would use? I said if you wanted I just gave you 4 numbers, right? I said if you want to make a 95% confidence interval, you're always going to use 1.96. If you're going to make a 90% confidence interval, you always use 1.645. And then I gave you a number for 80, 1.28, and for 99, 2.58. And I said those are the 4 numbers you need to know. You got to memorize those, and that was it. The T table, it's different, okay? So if you got numeric variable, you're using the T table. Okay. We use the T table. So what number do we use in a confidence interval? Okay, so for a confidence interval, what number will be our critical value? Well, we look at what level of confidence we want. So if we want 90%, we can see that there's actually a column that has 90% confidence. Okay? And then there's something called DF. DF is degrees of freedom. DF is degrees of freedom, and for most circumstances, your degrees of freedom is going to be n minus 1. Okay, actually, I thought it was going to be n minus 1. DF is equal to n minus 1. What is n?
Sample
size. So you do sample size minus 1. That's your degrees of freedom. So if we have a sample of 15 items, how many degrees of freedom do we have? 14. Good. Simple enough. Okay? So if we have a sample with n equals 15, degrees of freedom equals 14. And if I say we want a 90% confidence interval, what you're going to do is you're going to look at your table, look at the column that says 90%, and you're going to go to the row that says 14 degrees of freedom, and what's the value that we would use there? 1.761. Okay. Use 1.761. So our critical value, which we're going to call T star, is 1.761. Alright? And actually, if you look at the bottom, the very last row, where it says infinity, degrees of freedom infinity, those are actually the same numbers that you'd use for confidence intervals for proportions. So infinity for 90%, it's 1.645. For 95%, 1.96. And then I never gave you a number for 98, but for 99 you see it's 2.576. I just said use 2.58. It's close enough. But that's what we've got going on. Okay, so just another one. All right, so if I have, I take a sample of 10 people. All right, let's say the average weight is we'll say the average weight of, I don't know. Okay, the average weight is 190 pounds. The standard deviation is 42 pounds. And we want to make a 95% confidence interval. What T star do we use? Alright, so so just look it up in the table, try to figure this out. I'll give you 10 seconds. Be able to get your answer in 10 seconds. So T star is equal to, you guys figured out a number? 2.262. Is that good? Anybody confused on that? We have 9 degrees of freedom, right? Degrees of freedom is n minus 1. I have a sample of 10 people, so I use 9 degrees of freedom, 95% confidence, 2.262. Is that okay?
Yep.
Alright. Sometimes we have 2 samples. Okay? So last week we covered proportions, and sometimes we had 2 samples of proportions, right? We had the drug trials with Vioxx and nicotine gum or things like that, right? In those cases, you had 2 samples. Well, when you're dealing with numeric variables, you might also have 2 samples. So what do we do when we have 2 samples?
Times 2.
figuring out your t-star is actually just the same. You use n minus 1, and you look at your column for the confidence level. Okay. Same method, all right? But there's just one extra thing, all right? So degrees of freedom is equal to n minus 1, and use the column with the appropriate confidence. Alright. The only issue is when you have two samples, you have two n's. You have an n1 and an n2. Okay? So with two samples, we have an n1 and an n2. So which n do we use for our degrees of freedom? No, just use the smaller n. Okay? So if n1, you have a sample of 12, and n2 is a sample of 40, do 12 minus 1, 11 degrees of freedom. Is that okay? So use the smaller n. Okay? So if you have, so if n1 equals 12 and n2 equals 40, the degrees of freedom is going to be equal to 12 minus 1, 11 degrees of freedom. Any issues with that? And then so once you figure out you have 11 degrees of freedom, you figure out the confidence level that you want to use, you look down the column and figure out your t-star. That's not too bad, right? Okay, so that's figuring out your t-star. Okay. That applies for confidence intervals. So what's the other thing that we have to do? We have confidence intervals and we have hypothesis tests, right? Okay. So when you did, can I erase this? I already started. Okay, no objections. When we did hypothesis tests for proportions, okay? When we did hypothesis tests for proportions, we would look at the table, the z-table for what? The normal table to look up our
z-score.
Okay. Yeah, so we look up the z-score to get our p-value, right? So we look up the z-score, you go through the process, you find your standard error, you find your proportions, you take the difference, divide by the standard error. It gives you a z-score. When you have the z-score, you go to the normal table, and it will help you get your p-value. It's the thing you look up in your normal table isn't necessarily your p-value. Maybe you have to subtract 1. Maybe you have to double it. Okay, maybe you have to do both. Subtract 1 and then double. Okay, it depends on the circumstance. But you look it up in the normal table, and that will help you figure out your p-value. Alright? Same thing applies here. You're going to go through a process, and you're going to get not a z-score, but a t-score or a test statistic. Okay, and I'll teach you that process in a bit. Okay, but you're going to figure out a test statistic after you go through the steps, and then you look up your test statistic in the table to help you figure out your p-value. Sometimes you double it, sometimes you don't, okay? You don't really have to worry about subtracting from 1 when you're dealing with the t-table, okay? But the idea applies the same, all right? So for hypothesis tests, table to help us find our p-value. So basically, when you do your problem, and then you get a test statistic. Okay, it's kind of like a z-score. So you do the problem, you get a test statistic. Then you look up that test statistic in the table. It'll give you area, it'll give you a tail area, okay? And then if the test is one-sided, how do we know if a test is one-sided or not? Yes. If the test is one-sided, that means the alternative hypothesis has either greater than or less than. So if the test is one-sided, so HA has greater than or less than, the tail area is the p-value. If the test is two-sided, so that means the alternative has what?
Equal.
Not equal. Then double the tail area to get your p-value, okay? Then tail area times 2 equals p-value. Alright, so far so good, right? No major surprises here. It's very similar to what we do when we're dealing with proportions and the normal table. Alright, but this is where we use our table very differently. In the z-table, you had a number, you just round off to two decimal places, and you would look up a number. You would say, my z-score is 0.84. Then you look up 0.84 on the table, you get some number, and you walk along, go on your way. Having a party. End of school for them. Close to games. Alright, over here, it's a little bit different, okay? Let's say I have a problem where my degrees of freedom is 14. Okay? If my degrees of freedom is 14, let's say my degrees of freedom is 14, and let's say my test statistic equals 1.761. So I have 14 degrees of freedom, I do my math, my test statistic comes out to be exactly 1.761. Okay? Well, what this says, alright, go to that row that says 14, and we see 1.761. It says, okay, if your test statistic is 1.761, you draw a line at 1.761, how much will I have in my tail? Okay, can you guys see that? in the table. It's in the second column.
10%.
Huh?
10%.
Not 10%. You go to the very top, and it says T is 0.050. Okay? So it says T 0.050. That means I have 0.050 in my tail, or 5%. Okay? So I have 0.05 in the tail. So that's if my test statistic is exactly 1.761, I would have 0.05 in the tail. Is that okay? Alright. If I have 14 degrees of freedom, and I have a test statistic, I'm going to just write TS for test statistic, ends up being 2.145, how much do I have in my tail? I have 2.5%. Can we see that? I just want to make sure everyone can see that. Huh?
0.2.
Yeah, so, because the table says it's T.025, right? At the top. So ignore the confidence level thing, but just says the right tail probability. Did I write the wrong number?
Yeah.
No, 14 degrees of freedom, 2.145. If I draw a line at 2.145, I have 0.025 in the tail. Yes?
The test statistic is T-star, right?
No, this is, so T-star only applies when we're doing confidence intervals.
Okay.
Okay? When we're doing hypothesis tests, we have the test statistic, which I'm abbreviating to be TS.
Okay.
Okay? So if my test statistic ends up being 2.145, then that means I'll have exactly 0.025 in the tail. Is that okay? Alright, so this is, so if I have degrees of freedom 14, and let's say my test statistic ends up being 1.94. How much will I have in my tail? Alright.
Between.
Yeah. So 1.94 is bigger than 1.761, but it's smaller than 2.145. Okay? So it says if I drew a line at 1.761, how much would I have in my tail? 5%, right? But then if I go further away from 0, and I go to 2.145, how much will I have in my tail? 2.5%. So if I go somewhere in between, let's say 1.94, how much will I have? Well, the answer is I don't know the exact number. I don't know the exact number, but I do know my tail is going to be more than what? 0.025 and less 0.05. Okay, so we don't know the exact value. Exactly how much is in the tail. But we know that the tail is less than 5% and more than 0.025. Is this notation okay? Where I have 0.05 is bigger than the tail, which is bigger than 0.025. Alright? Or in other words, the tail is between 0.025 and 0.05. Does that make sense for everyone? Okay. So actually, most of the time, your answer is going to be my tail area is between this and between this, because the only way you're going to get exactly 0.025 is if your test statistic ends up being exactly 2.145 with 14 degrees of freedom. Generally, you're not going to get exactly this number. So anytime you get a number that's in between the values here, your tail area is going to be in between the areas at the top of the columns. Okay? Alright, so let's just try a couple practice problems.
Okay.
And you tell me how much is in the tail. Alright? And once you figure out the tail area, then you can figure out your p-value by either doubling it or leaving it depending on your alternative hypothesis. But we got to know how to use the table to figure out our tail area first, and then we can worry about the p-value. Alright, so let's say we have 18 degrees of freedom, and my test statistic ends up being 2.36. 2.367. Okay. And then to figure out your tail area here, how much is in the tail? Let's say I have degrees of freedom. Okay, well actually, let's just start off with that. Okay, let's just start off with that. So I'll give you guys a few seconds to work on that. Don't shout out your answer. Okay, so when you think you got your answer, just look up at me. Or just look up. Alright.
Yeah. So we were just saying.
Okay, we ready? My tail area. We know it is smaller than 0.025, but bigger than 0.01. 0.010 if you want to be add extra unnecessary zeros. Okay, is that alright?
Yes.
Did anyone not get this or anyone confused? Don't be shy. Alright. Well, I know some of you probably didn't get it, so no shame, alright? I'm just going to copy the relevant row. So with 18 degrees of freedom, okay, the values for 18 degrees of freedom, I'm just going to start at the second number. I've got 1.734, 2.101, 2.552. Okay, and 1.734 is T.050, and this is T.025, and this is T.010. Okay, the number that I have, 2.367, is in between 2.101 and 2.552. It's bigger than this number but smaller than this number, which means the amount I have in my tail is going to be in between this number and this number. So it's going to be bigger than 0.01 and smaller than 0.025. So that's how I got this to be my tail area.
And do you have to mark up your curve?
Oh yeah, I should. Okay, so I can just write 2.367, and my tail is less than 0.025, bigger than 0.01. Okay, so as long as your arrow, the greater than or less than signs are pointing in the correct direction, you can have it go least to greatest or greatest to least. It doesn't matter. These two things are saying the exact same thing. Alright. Alright, so you guys are discussing stuff. Do you have a question? Are you sure?
I think I get it.
You got it? Okay, we'll try another one, okay? This table only has positive values, alright? And that's because the thing is symmetric, Okay, the t-table or the t-distribution is symmetric. So if you ever get a negative test statistic, you just drop the negative and look up the positive, okay? And the only thing is that the tail is going on the other side of the table. It doesn't really matter, but just to make sure that we understand, let's say we have degrees of freedom equal to 20, and my test statistic ends up being negative 3.87. Negative 3.87. How much do I have in my tail? Okay, so work on this for a second. We've got 20 degrees of freedom, and our test statistic is negative 3.87.
We're gonna have a look at.
It can be done. It can be done.
Can we done?
It can be done.
Oh, alright.
So how much will be in my tail? Less than 0.001. Okay? I don't know how I don't have a number that is bigger than, but I do know it's going to be less than 0.001. Okay, let's see how we did that, all right? So at 20 degrees of freedom, okay, my test statistic is negative 3.87, but I said whether it's negative or positive, just drop the sign and look up the positive, okay? So the relevant numbers here, I've got 2.845. I'm just going out to the end of the table. I've got 2.845, 3.552. And this corresponds to 0.005, and this is 0.001. Okay? Where is 3.87 on this? 3.87 is bigger than 3.552. Okay? So what this is saying is that if I drew a line out at 3.552, how much will I have in my tail? I will have 0.001. But I'm not drawing a line at 3.552. I'm going even further away from 0. So how much am I going to have in my tail? Even less than 0.001. Okay? Because at 3.552, I only had 0.001. Okay? But you can see that if I get even further away from 0, I'm going to have even less and less. Okay? So the amount in my tail is less than 0.001. Is that okay? If you write the amount in your tail is more than 0.001, that's wrong. Okay? Because the further you are from 0, the more extreme your test statistic is, the smaller the area is in the tail. The tail gets smaller and smaller as you get further away from 0.
But if it's negative.
Yeah, so we had a negative, right? Again, I said just ignore the negative, okay? So what the thing is saying is if I drew a line at 3.552, I would have 0.001 in this tail. And if I go even further away from 0, how much am I going to have over here? Less than that. So if I'm going to 3.87, I'm going to have even less than 0.001.
So if it's negative, you would draw it on the left side.
Yeah.
Okay.
Okay? But the fact is, the farther away we get from 0, we're going to have less in the tail. If we're closer to 0, we're going to have more in the tail. Is that okay?
Yeah.
All right? And then here's the last rule. Well, I just want to make sure that everyone's okay with this before I go on. Yes, question? No. If it was positive 3.87, the area in your tail is also going to be less than 0.001.
But on the right side.
it would be on the right side of the picture. Okay, here's the last thing. Sometimes you won't find your degrees of freedom in the table. So let's say you have a sample of 37 items, you would have 36 degrees of freedom, and you don't see 36 degrees of freedom on the table. Okay? If you're ever in that situation, if you can't find your exact degrees of freedom on the table, always round down. Okay? So even if you have 39 degrees of freedom, you will round down to use 30 degrees of freedom. If you have 47 degrees of freedom, round down to use 40 degrees of freedom because you have 40 in the table. Okay? So if you can't find the exact DF, always round down to the closest DF that you can find. So round down to closest DF. Alright, so let's try this out. Let's say you have 57 degrees of freedom, and your test statistic ends up being 0.92. You end up getting a test statistic of 0.92. How much is going to be in your tail? Okay, so the amount in our tail is going to be what?
More than?
It's going to be more than 10%. More than 10% implied always, the tail is always going to be less than 1. But in this case, it'll be more than 10%. So how do we do this? So when we go to our table, we're going to use degrees of freedom 50. Okay? And then the very first number that we have is 1.299, and that corresponds to a tail area of 0.10. The next number, T.050, I've got 1.676. Okay, my test statistic is 0.92. 0.92 is smaller than 1.299. So that says if I drew a line at 1.299, I would have 10% in my tail. But I'm not drawing a line at 1.299. I'm closer to 0 at 0.92. So how much is going to be in my tail? More than 10%. So the amount in my tail is going to be more than 10%.
Oh, and that's just because it's in the 0.10 T column, right?
Sorry?
Okay.
Yeah, closer to 0. Are we okay with the use of the t-table? Okay, because you will be using this for all of chapter 9. Okay. Actually, anytime you're doing confidence intervals or hypothesis tests for numeric variables, you will always use the t-table. Okay, no exceptions. Always use the t-table. Confidence intervals and hypothesis tests for numeric variables. Common mistake. I see people trying to look things up in the z-table. Okay, wrong. Alright, so let's do our first bit, okay? Let's do confidence intervals for means based on one sample. So when we make a confidence interval, what are we trying to do? We observe a sample, and we're hoping that this sample is representative of the population. Based on what we understand about sampling distributions, we say, well then I'm this amount confident that the population has this property. When we dealt with categorical variables, we looked at a sample. We saw maybe our sample was 30%, whatever, okay, 30% of this category. We said, based on our sample, I'm then 95% confident that my population is, you know, between 30% plus or minus 3%. So you can say I'm 90% confident that the population proportion is between 27 and 33%. Okay, so based on what we see in the sample, we make a confidence interval, we give ourselves a margin of error, and we say we're confident that the population proportion is in between this range. We're going to do the same thing, but for numeric variables. Okay, so we're going to observe a sample. If we're dealing with numeric variables, what will be the properties that our sample has? We're going to find a sample mean and a sample standard deviation. Okay, so based on my sample mean and sample standard deviation, I'm going to make a statement about the population mean. Okay, we're not going to try to make statements about the population standard deviation. So based on what we see in our sample, we're going to make a statement about the population mean. Based on what we observe in a sample, we'll make a statement What is the symbol for sample mean? No, not mu. X bar. Sample mean is X bar. Sample standard deviation is S. And sample size?
N.
N. Okay, so we're going to have an X bar, an S, and an N. And what is the symbol for population mean? That's mu. Okay, so we're going to use X bar, S, and N to make a statement about mu. Okay, so if we want a confidence interval for mu, X bar forms the center of our interval. Okay, this goes in the center of the interval. This is our best guess for mu. And then we go plus or minus the margin of error. The margin of error is going to be the combination of our critical value t star times the standard error. So this is called margin of error. Yes, question? Did you have a question?
Oh, no, I'm
No.
distracted.
Okay. You got it. Okay. Alright, so this seems kind of familiar, right? When we did a confidence interval for P, we just used P hat here, and then instead of T we had Z star times the standard error. Okay. A lot of you did well on the confidence interval problems. Okay, so the standard error here, so the standard error for numeric variable one sample mean is going to be S over the square root of N. It's not P times 1 minus P over N or whatever like that. S over the square root of N. That's it. Simple. So when you put everything together, you've got X bar plus or minus T star times S over the square root of N. This is the standard error. That's your margin of error. T star is your critical value. And your interpretation of a confidence interval for a numeric variable is very, very similar to an interpretation for confidence interval for proportion or categorical variable. Alright? So we don't have to spend that much time on it, but we'll do an example just to make sure we understand. Okay. So let's say we want to make a 90% confidence interval for the mean height of an NBA player. Okay. We take a random sample. Of 30 players. 6'5"? Sure. Okay. 6'5", so that's 77 inches. With standard deviation equal to, we'll say, 3.1 inches. That's probably too big, but whatever. All right, make a 90% confidence interval. For the true mean height of NBA players. Did someone forget their calculator in my office? No. You did? That was yours. Alright, do we have an answer? I'm getting 76.04 to 77.96. So basically 76 to 78 inches. We did not get that? You got that? You did not get that far. Okay, I'll give you another minute. Huh?
That far.
Not that far. Okay. Keep trying. Keep trying. I'll give you another minute.
How do you use the table?
How do you use the table?
I don't know how to use the freedom.
That's the standard deviation.
Oh. God.
Might be right. I find it's still not there.
All right. Well, let's go over this, okay? If you didn't finish by now, that's okay, I guess. But get better so you can do it. All right. What is my x bar? Let's just list off the things we know. X bar is
77.
77. What's s?
S
Three
is
point-
3.1.
3.1. What's n?
30.
30.
30, okay.
Square root. Well, in the thing.
Alright, and what is my t star?
1.699?
1.699. Alright, is everyone
9.
okay with getting all of these numbers?
Okay, now I am.
Yes, Marcella. How did I get 1.699? How did I get 1.699? Okay,
You
how
looked
many
up.
degrees of freedom do I have?
29.
I'm asking Marcella. You don't, no? Okay, degrees of freedom is n minus 1. Okay? Degrees of freedom is n minus 1. So then I have 29 degrees of freedom. That tells me which row to look at in the table. Okay? And then what is my level of confidence that I want to use, Marcella? 90%. So I look at the row 29 degrees of freedom and I go to the column corresponding to 90%, and we see that number is 1.699. Okay? So that's how I get my t star.
Alright.
Okay, everyone is good with that?
Oh,
Okay? So now, so all you have to do is read the problem carefully, figure out these 4 numbers, and the rest is just plugging them into this equation. And you go 77 plus or minus 1.699 times 3.1 divided by the square root of 30. When I did that, I got 77 plus or minus 0.9615 or something? 0.9616? I don't know, something like that. Yeah?
so it was
Yeah.
1.
Okay, so I got 77 plus or minus 0.962, 0.9616, whatever. I just rounded off to 0.96. It doesn't. If you want to keep 4 decimals, 77 plus or minus 0.9616. So on the high end, you get 77.9616, and on the low end, you get 76.0384. Okay, so this, depending on where you want to round, will round to basically 76 and 78 inches. Okay, I don't know how precise you want to get. Okay, so we are 90% confident that the average height of all NBA players is in between 76 and 78 inches. And there you have it.
Don't erase it.
Okay?
No. Hold on.
No? Well, not, so let me, I'm just going to put the interpretation, and then, because the interpretation is still the same, you'd say I am 90% confident that the mean height of all NBA players is between 76.04 inches and 77.96 inches.
Where did you get those? I got up to 9.9616. And then you pulled up 77.9616.
So I did 77 plus 0.9616 and 77 minus 0.9616. Okay?
Thank you.
Right? So your confidence interval should always have 2 numbers. That was, for, you know, some of you who got your confidence interval questions wrong, some of you just gave me 1 number for a confidence interval, okay? That's not going to work, right? An interval means you've got a low end and a high end. That's the definition of an interval. So there's a low and a high. So if you just give me 1 number, that's not an interval, that's just a number. So that's my interpretation. What if I ask the question, do we have evidence that the mean height not 6'7", okay, which is equal to 79 inches. Do we have evidence that the mean height is not 79 inches? And the answer is yes. We have evidence that it's not 79 inches. Why?
It's not in between
Because
those.
79 is not within my interval, okay? 79 is not within the interval. So we have evidence that the mean is not 79, or that the mean is different from 79. Yeah.
So we know that this is a numeric problem
Just
because height is numeric?
Yeah, because height is a numeric variable.
On like the test if we get,
Well-
choose between two, like which table
Right.
we're using.
Yeah, yeah.
You
Well,
have to know which
okay.
variable.
I mean, there should be some key things that will tip you off that this is not dealing with proportions, okay? Because you're either going to be dealing with means or proportions, okay? So as you read this, it says things like the mean height is 65 inches. So that should be a tip off. Oh, we're dealing with a mean height. I'm dealing with a numeric variable, okay? But yeah, height is a numeric variable, so we're dealing with the mean height, okay? But let's say for some reason you thought you were dealing with a proportion. So you should try to start off your proportion, right? So when you do a proportion, you've got to have a p hat, right? What number are you going to use as your p hat, okay? Somebody might try to use 3.1, okay? Basically, your p hat, a proportion always has to be between 0 and 1, okay? Tail areas, p-values, all of those things are probabilities. They must be between 0 and 1. So as you're doing problems, if you get a p hat that's bigger than 1, you know you did something wrong. You should stop and try to figure out what you've done wrong. Because, you know, as I went through quizzes to grade them, I noticed some of you didn't, you had p hats or p's bigger than 1, and it just doesn't work, okay? So your p hat has to be less than 1. So there's no number here that's smaller than 1, unless you wanted to use 90%. But you should know that the 90% corresponds to the confidence interval, so that's not going to be your p hat. Okay?
which also tells you.
Huh?
Which also tells you, because you're asking for the confidence interval, right?
Well, confidence interval, that could work for either p or mu, okay? Because we have confidence intervals for proportions as well. All right, is that okay? All right.
This is high. Wait, sorry. It's way.
height.
The 70, like,
height in
high.
measures.
Would you want
So is it
us to draw the curve for that, or not necessarily?
You don't have to make a curve for
Well,
a
you
confidence
also
interval.
get numbers in the other problems.
All right, let's do a hypothesis test, okay? This is a hypothesis test for mu. Okay. We're dealing with numeric variables, one sample. After we work through this, we'll take a break, and then we'll do numeric variable stuff for 2 samples. Which I know you guys are excited about, yeah. All right, hypothesis test. you always start off by writing hypotheses, right? So when you deal with proportions, what will you put in your hypothesis? It was either P equals this or P doesn't, okay? Equal that thing, or P is greater than or P is less than. And then when you had two samples, you had P1 and P2 and things like that. Hypothesis test for mu with one sample, your hypothesis, your null hypothesis is going to be mu equals some number, whatever that number is, okay? I'm going to just make up a number. We'll say 145. Mu equals 145, and then the alternative is that mu either is not equal to 145 or mu is greater than 145 or mu is less than 145. You know, your choice of whether to choose greater than, less than, or not equal to, it all depends on how the question is written, right? So it depends on how the question is written. You're going to read through the problem, and as you read through the problem, you're going to have to pick out x bar, s, and n. So identify x bar, s, and n as you read the problem. Once you figure out x bar, s, and n, your test statistic is equal to x bar minus the mu. The mu comes from the null hypothesis, okay? X bar minus mu divided by the standard error. Okay? And the standard error is equal to S over the square root of n. Okay. So far this is all okay, right? There's nothing here that's mind-blowing. Okay? And then once you have your test statistic, what do? You look it up in the table, okay? So with the test statistic, look it up in the t-table. Okay, and you get your tail area to find the tail area. And based on the tail area and your alternative, you get your p-value. You either leave it the same when you have a one-sided test, or you multiply the tail area by 2 when you have a two-sided test. Okay? So then figure out the p-value. So the p-value equals the tail for one-sided tests. P-value is equal to 2 times the tail for two-sided tests.
Two-sided test.